Hi, I'm Jessica Rigley and I'm a PhD student at the University of Cambridge. And today I want to talk about exozodiacal dust and why it matters for the LIFE mission. So as you likely know, the zodiacal cloud is a diffuse complex of interplanetary dust which lies in the inner solar system. And it goes all the way from a few solar radii to a few AU from the sun. And there are many sources of zodiacal dust, including asteroids, comets, the interstellar medium, and the Kuiper belt, although the main source of zodiacal dust is believed to be the spontaneous disruption of Jupiter family comets. And the zodiacal cloud actually dominates the thermal emission in the sky, which means that it will be a significant source of noise for the LIFE mission. For example, this is the infrared emission seen by COBE, and in blue, you can see the 25 micron emission. And we see this S shape, which is due to zodiacal cloud particles lying in the ecliptic plane. So around 20% of nearby A to K stars show excess emission in the mid and near infrared, which we attribute to warm dust and hot dust. And we call this exozodiacal dust in analogy to our zodiacal cloud. And throughout this talk, I'm going to focus on the warm exozodiacal dust, which is seen in the mid-infrared and is believed to lie in the habitable zones of stars. For example, this shows the fraction of stars which have a given level of excess emission in the mid-infrared, and the zodiacal cloud's level is quite low, so the zodiacal cloud is around 0.01%, whereas the levels that we detect with observations are roughly 100 or even 1,000 times brighter than this. And when we compare our observations with an in situ model, so this dashed line shows a model where you have an in situ asteroid belt, we underpredict the incidence rate of exozodiacal dust, which means that we need to find another mechanism to explain how this dust is there. And the problem is, because everything's so close to the star, the timescales are very short. So we need something which can either supply dust close to the star on short timescales or somehow extend the lifetime of the dust. And exozodiacal dust is important for two main reasons. The first reason is that it gives us a unique way to study the inner regions of planetary systems. And by understanding what's going on with the dust, we can learn something about the underlying planets in the system. And the main thing I want to talk about today is that exozodiacal dust is a source of noise and confusion when we're trying to detect and characterize Earth-like planets. In particular, it may affect which biosignatures we're able to see. For example, this shows for HabEx and LUVOIR-like missions, how the yield of exo-Earth detection missions would be affected by the level of exozodiacal dust seen around other stars. And we measure the levels of exozodiacal dust in this unit of zodis, where one zodi is the zodiacal cloud. And another reason that this dust is important is that we expect that planets embedded in the disk may create structures in the dust. So for example, this is a simulation from Defer et al, where if you have an Earth-like planet orbiting a Sun-like star at 1 AU, as we dial up the level of dust, the signal from the planet disappears and gets obscured by the dust. However, when we get to 20 times our zodiacal cloud, instead of seeing the planet signal, we actually see this other signal, which is due to a clump of dust. And so we can get false positives. And exozodiacal dust was first detected in the mid-infrared using photometry. However, photometry is limited to detecting excesses of a few percent of the star, so it means we can only really see the really brightest exozodis. For example, Spitzer found that 1% of stars have exozodis brighter than around 1,000 times our zodiacal cloud. And for these really bright systems, which are quite rare, we think that they should be due to transient phenomena. So there are two possible origins I put here. The first one is dynamical instabilities. So this is things similar to the purported late heavy bombardment of our solar system, where you have lots of comets scattered into the inner planetary system at the same time. However, models have shown that even if every single planetary system undergoes an instability at some point in its lifetime, they're still too short-lived to explain these exozodis. So another possibility is giant impacts, which we expect to occur in the late stages of terrestrial planet formation. For example, this shows a simulation of how it would appear if we looked at James Webb, where a system's undergoing giant impacts. So to see what's going on with fainter exozodi, we have to use nulling interferometry in the mid-infrared. And there are two instruments which have been used to survey this dust. The first one is the Keck interferometer nuller. And this had a sensitivity of around 150 zodis and detected this dust around 11% of stars. And then the instrument which we still use today is the Large Binocular Telescope Interferometer. And this has a sensitivity which depends on the spectral type of the star, but is around 20 to 50 zodis. And at this level, they detected warm exozodiacal dust around 26% of stars. Oops. So this just summarizes the findings from the host survey. So the host survey used LBTI to survey 38 nearby main sequence stars and detected the dust around 10 of them. And when they fitted the best fit median zodi level, they found a value of 3 zodis, which is actually quite low. However, it's also very uncertain. So the 95% upper limit of the median zodi level is 27 zodis. And I just wanted to highlight two key results from the survey. So the first one is shown here, which shows the detection rates for different categories of stars. And when we consider systems which have cold dust, which is indicative of Kuiper belt analogues further from the star, we find a really strong correlation between the presence of Kuiper belts and warm exozodiacal dust. So of the 9 stars in the host survey, which have cold dust, 7 of those also had warm dust. And then this shows the detected level of exozodiacal dust versus the age of the star. And while we do detect this dust around some younger systems, we're also seeing it around systems which are gillion years old. And so it's been found that there's actually no correlation with the age of the star or its spectral type. So this begs the question, what's the origin of this dust? And given this really strong correlation between the presence of cold dust and warm dust, it's possible that the dust is produced further out of the planetary system and somehow transported in towards the habitable zone. And so I've illustrated that here in this diagram, where this shows the size of things versus the distance from the star. And if we have a planetesimal belt at tens of AU from the star, then we're going to have lots of kilometer-sized bodies similar to comets, and these will collide together to produce smaller and smaller things until they produce dust. So we'll also have lots of dust grains in this outer belt. And this dust can migrate inwards due to Poynting-Robertson drag, which is essentially a component of radiation pressure that causes particles to spiral in slowly towards the star. And so dust produced in the collisions in this belt can then drift inwards and be delivered to the habitable zone. And the second mechanism is exocomets. So if these comets are scattered in by planets, when they get close to the star, they can then spontaneously fragment and produce dust, which would also supply the exozodiacal cloud. So this summarizes the results from PR drag models. So this is what a typical radial profile of dust would look like to a PR drag model. So this is the density of dust versus distance from the star. And for example, if this is where the planetesimal belt is, you have a given density of dust. And then as you go inwards of the belt, you see a sharp drop in the density of dust. And then as you get closer in, it flattens out and you get a roughly flat, constant radial profile all the way in towards the star. And so this means that PR drag can produce relatively low levels of dust. So for example, we modeled this in Rigley and Wyatt 2020. So this shows the excess emission at 11 microns versus how far away from the star the outer belt is. And I've shown it for different masses of the belt and different spectral types. And also shown on here are the 9 stars from the host survey, which are known to have outer belts. And the key finding is that while some of these stars have exozodiacal dust levels which could potentially be explained by PR drag, a lot of these systems have far too much dust, which means that we need another mechanism to explain the detections. However, if a system does have an outer belt, these PR drag models mean that we should be seeing exozodiacal dust. So if we don't see the dust, we can then learn something about the planetary system. For example, Sigbu and Tau Ceti both had non-detections of dust despite having outer belts. So it's possible that in these systems, as the dust migrates in towards the habitable zone, it's being removed by intervening planets. So it's also possible that exocomets can be scattered in towards the habitable zone. And this requires a chain of planets, basically. So it's highly dependent on the planetary system architecture, and models have shown that the most efficient way to do this is if you have a chain of closely spaced, low-mass planets, which are roughly tens of Earth masses. For example, if we had a really massive Jupiter-like planet, then this would probably eject all the comets rather than scattering them inwards. But there are some cases where we think this has to be the mechanism. For example, Eta Corvi has an exozodi which is 2,000 times our Zodiacal cloud. And so we think that must be due to comets being thrown in. And one reason it's really important to model this mechanism is that if we do have comets being thrown in towards the inner planetary system, then it's really likely that they're going to bombard planets in the habitable zone, and this will determine their habitability. For example, the comets may deliver key volatiles such as water to the planets, or they may instead deplete the atmospheres of those planets. And exocomets are also a promising source of exozodiacal dust because we believe that the zodiacal cloud is mostly sustained by the spontaneous fragmentation of Jupiter family comets. For example, we modeled this in Rigley at White 2021, and this shows the brightness of the zodiacal cloud that a distant observer would see versus time. And if the zodiacal cloud or an exozodiacal cloud is being sustained by comets, then the brightness of the dust should be really stochastic because it will depend on the sizes of comets which are scattered in and their dynamical lifetimes and how long they spend in the inner planetary system. Because if they spend more time in the inner planetary system, they have more time to produce dust. And so this means that if exozodis are cometary, then we can expect to see a whole range of levels of brightness. So what does this all mean for life? So of course, exozodiacal dust, because it lies in the habitable zone, will be a source of photon noise when searching for Earth-like planets. And in Kwan's et al., when they modeled the contributions of different noise sources, they found that on average, exozodis would be around 5 to 10% of the total noise budget, with stellar leakage and the zodiacal cloud contributing more. However, this assumes that the exozodis are smooth, face-on, and centrally symmetric, with a median level of 3 zodies, which is potentially a bit optimistic, depending on the uncertainties in the survey. And this is actually a really important point, that if exozodis are centrally symmetric, then yes, they can be removed by the phase chopping of the interferometer. However, this won't always be the case. Another unknown is that we haven't actually detected any exozodis around M stars yet. So we haven't been able to detect them with photometry, and we haven't been able to resolve them with interferometry, which means at present, we don't know anything about the distribution of exozodiacal dust around these stars. So one key reason that exozodis will be important is that if we have planets embedded in an exozodiacal disk, then we expect that they will produce asymmetries in the dust, things like rings, clumps, and offsets. For example, if you have particles migrating in towards a star by PR drag, and they pass through a mean motion resonance of a planet, then they will get trapped there. And this will give you local enhancements in the density of dust. For example, we've seen this in our own zodiacal cloud with the Earth's resonant ring, where you have a clump of dust trailing Earth on its orbit. And this shows a simulation from Defer et al. So this is for a 10 Zodi disk with an Earth-like planet orbiting at 1 AU from a Sun-like star. And here the inclination of the disk is varied from face-on to edge-on. And this is the thermal emission, and this shows the asymmetric brightness distribution. And depending on the inclination of the disk, the tolerable level of exozodiacal dust was found to vary from 15 zodis for a face-on disk to 1 zodi for an edge-on disk. And this is because the more inclined the disk is, the more pronounced the asymmetries become. And so this is something that we really need to understand better when we look for planets for life. So in conclusion, exozodiacal dust is a really important source of noise because it lies in the habitable zones of stars. And while centrally symmetric exozodis can be removed by nulling interferometry, asymmetric structures won't fully be removed and could cause confusion. And we need more models and observations, especially around M stars, to fully understand how exozodis are going to impact life. Thank you for listening.